You are tuned to Iri-e-learning, and I am your host, Teacher. In this structure and bonding lesson, we will examine covalent bonding. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to state the types of atoms involved in covalent bonds, explain the formation of covalent bonds, draw dot and cross diagrams to illustrate covalent bonding. We will do a quick recap before proceeding with the lesson. Atoms bond to obtain a stable electron configuration. The first 20 atoms are stable when all the shells contain their maximum number of electrons. That is, there are 2 electrons on the first shell and a maximum of 8 electrons each on the second and third shells. Atoms acquire a stable electron configuration by losing, gaining, or sharing valence electrons. Recall, valence electrons are simply the electrons on the last shell. As we learned in a previous lesson, ionic bonds are formed when atoms lose, that is donate, and gain, that is accept valence electrons. However, in this lesson, the focus will be on covalent bonds, in which the atoms share valence electrons. Now we can proceed with the details about covalent bonds. What type of atoms are involved in covalent bonding? Covalent bonds occur between nonmetal atoms only. How do we identify nonmetal atoms? These are the atoms with greater than 3 electrons on their last shell. These include atoms from groups 4, 5, 6, and 7. Recall that the atoms in group 0 are already stable and rarely or do not participate in chemical bonds. However, there is an exception to the rule of identifying nonmetal atoms. The exception is hydrogen. Hydrogen has a single shell with 1 electron. Therefore, it actually has less than 4 electrons on the last shell. However, it is a nonmetal, as we recall from a previous lesson that atoms with only 1 shell are classified as nonmetals. When dealing with covalent bonds, never forget that the nonmetal atoms share their valence or outer shell electrons. There are 2 important things we need to know about how the atoms share their valence electrons. The first one is that they only share the number of electrons they need to become stable. And secondly, the atoms will only share an equal number of electrons with each other. So if atom A shared 1 electron with atom B, then atom B will share back only 1 electron with atom A. So what is the binding force in a covalent bond? The binding force is the attraction between the nuclei of the atoms involved in the covalent bond for their shared electrons. So here we have the shared electrons. We have the nucleus of atom A and the nucleus of atom B. And the attraction is the nuclei of both atoms pulling on those shared electrons. Now it's time to draw dot and cross diagrams to illustrate covalent bonding. The first example is fluorine. Fluorine has the chemical formula F2. That is, 1 molecule of fluorine consists of 2 fluorine atoms bonded together. We will illustrate how to draw dot and cross diagrams following a step-by-step approach. So step 1, we will record the symbols and the electron configurations for the atoms involved in the bonding, and of course in this case it would be fluorine. So we'll take a quick look at the periodic table to obtain this information. Fluorine symbol F is found in period 2, which means that fluorine has 2 shells, a first shell and a second shell. On its last shell, it would have 7 electrons because fluorine is in group 7. As a result, the electron configuration for fluorine would be 2, 7. We can now record the information for the 2 fluorine atoms. Note that fluorine has greater than 3 electrons on its last shell. Therefore, fluorine is a nonmetal atom. In fact, fluorine has 7 electrons on its last shell, and the first shell contains its maximum of 2 electrons. Step 2, we will draw the nucleus and the empty shells of the atoms involved in bonding with their outer shells overlapping. Step 3, fill inner lying shells with electrons. Note that both fluorine atoms contain contain one inner-lying shell, which is the first shell that contains 2 electrons each. Recall that the dot and the cross are used to distinguish between the electrons of atoms involved in bonding for explanation purposes only. In reality, all electrons look the same. Step 4. Place bond or shared electrons in the overlapping region, then put any remaining electrons on the shell outside of that area. Note that an atom of fluorine has 7 electrons on the last shell, and we're actually going to draw the electrons for both fluorines, all 7, 1, 2, 3, 4, 5, 6, 7, and the same for the fluorine on the right. Now, since fluorine has 7 electrons on the last shell, we know from the electron configuration rules that the second shell can hold up to a maximum of 8 electrons, which means that fluorine needs only 1 more electron to become stable. And if we recall, an atom will share only the number of electrons that it needs in order to become stable. And since fluorine only needs 1 electron to become stable, it will share 1 of its 7 electrons with the other fluorine atom. After sharing 1 of its 7 electrons, fluorine has 6 electrons remaining, which will be placed on the valence shell outside of the overlapping region. Now to the fluorine on the right side of our screen. If the first fluorine shared 1 electron with the second fluorine, then the second fluorine will share back 1 electron with the first fluorine. After sharing 1 of its 7 electrons, the second fluorine now has 6 electrons remaining, which are placed on the shell outside of the overlapping region. At this point, all the valence electrons for both fluorine atoms have been placed on the valence or last shells. Step 5, we're going to count to ensure that each atom involved in the covalent bond has the maximum number of electrons on their last shell, because remember, the inner lying shells already contain their maximum number of electrons. Whenever we're counting the electrons on the valence shell, the shared electrons are counted for both atoms. We will start by counting the valence electrons for the fluorine on the left of our screen. 1, 2, 3, 4, 5, 6, 7, 8. The fluorine on the left now has 8 electrons on its last shell. As a result, its electron configuration is stable at 2, 8. We will do the same for the fluorine on the right. 1, 2, 3, 4, 5, 6, 7, 8. So the fluorine on the right also now contains 8 instead of 7 electrons on the last shell, which gives it a stable electron configuration of 2, 8. Step 6, represent the covalent bond as a stick diagram. Note that each pair of shared electrons is a covalent bond, and we represent that by a bold line drawn between the symbols of the atoms involved in bonding. Next, we will record the symbols of the atoms in the order in which they bonded in the illustration. A space is left between them to insert the number of covalent bonds that are formed between the 2 atoms. So let's check to see how many pairs of shared electrons were involved in this bond. And as we can see, there's only 1 pair, and as a result, we draw 1 bold line between the symbols of the fluorine atoms. And when we have 1 covalent bond between 2 atoms, we call that a single bond. Note that only the valence electrons, those are the electrons on the outer shells, participate in bonding. Therefore, we could illustrate the dot and cross diagram for the covalent bond without drawing the inner lying shells of the electrons as shown on the screen at this time. We have now completed the first example of covalent bonding, which illustrates the formation of the single bond. The second example is oxygen, and oxygen has the chemical formula O2. So therefore, a molecule of oxygen consists of 2 oxygen atoms bonding together. Following the steps, to step 1, we will record the symbols and the electron configurations of the atoms involved in bonding. So we're going to take a quick look at the periodic table to obtain this information. Oxygen has symbol O, and it's found in period 2, which means that it has 2 shells. The first shell, which will hold its maximum of 2 electrons, and the second shell, which is the last shell, will contain 6 electrons because oxygen is in group 6. As a result, the electron configuration for oxygen is 2, 6. Now we can record the information for the 2 oxygen atoms. Note that the oxygen atoms have greater than 3 electrons electrons on their last shell. Therefore, oxygen is a nonmetal atom. In fact, oxygen atoms have 6 electrons on the last shell and contain a maximum of 2 electrons on the first shell. Step 2, draw the nucleus and empty shells of the atoms involved in bonding with their outer shells overlapping. Step 3, fill the inner lying shells with electrons. Note that both oxygen atoms contain one inner lying shell, which has a maximum of 2 electrons each. Step 4, place the bond or shared electrons in the overlapping region, then put any remaining electrons on the shell outside that area. Note that each oxygen atom has 6 electrons on the last shell. To provide a visual, we will place the 6 valence electrons to the side of the information for the atoms. Based on the electron configuration rules, the second shell is stable when it has a maximum of 8 electrons. Therefore, oxygen would need 2 more electrons to become stable. Recall, the first condition for forming a covalent bond is that an atom will only share the number of electrons it needs to become stable. Since oxygen requires 2 electrons, then the oxygen will share 2 of its 6 electrons. The 2 shared electrons are placed in the area where the shells overlap. After sharing 2 of its 6 valence electrons, the first oxygen now has 4 electrons remaining, which are placed on the shell outside of the overlapping area. The second condition for forming a covalent bond is that atoms always share equal number of electrons with each other. Therefore, since the first oxygen shared 2 electrons with the second oxygen will share 2 of its 6 electrons with the first oxygen, and once again, those shared electrons are placed in the region of overlap. After sharing 2 of its 6 electrons, 4 electrons remain, and these are placed on the area of the shell outside of the overlapping region. At this point, all the valence electrons for both oxygen atoms have been placed on the last shells. Step 5, count to ensure that the last shell of each atom involved in covalent bonding contains the maximum number of electrons. Remember, the inner lying shells already contain their maximum number of electrons. Recall that the shared electrons are counted for both atoms sharing them. Starting with the oxygen atom on the left, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the first oxygen atom now has a maximum of 8 electrons on its last shell, resulting in the stable electron configuration of 2, 8. We do the same for the oxygen atom on the right, 1, 2, 3, 4, 5, 6, 7, 8 electrons. The second oxygen also contains 8 instead of 6 electrons, and now it has the stable electron configuration of 2, 8. Step 6, representing the covalent bond as a stick diagram. Recall, a pair of shared electrons is a covalent bond represented by a bold line. Next, we write the symbols of the atoms in the order in which they bonded in the dot and cross diagram. Make sure to leave sufficient space between the symbols to record the number of covalent bonds formed between the atoms. Let us check to see how many pairs of shared electrons occurred between the 2 oxygen atoms. As we can see, there's 2 pairs of shared electrons. Therefore, we draw 2 parallel lines where each parallel line represents a pair of shared electrons between the oxygen atoms. When 2 covalent bonds exist between 2 atoms, it is called a double bond. Also remember, the dot and cross diagram can be represented without the inner lying shells with electrons as shown on the screen at this time. So we have now completed the second example of covalent bonding, which illustrates the formation formation of the double bond. The third example is a molecule of nitrogen, which consists of two nitrogen atoms bonded together. For step 1, we will use the periodic table to get the symbol and electron configuration for each nitrogen atom. Nitrogen, symbol N, is found in period 2, which means that nitrogen has two shells. The first shell, which would have its maximum of 2 electrons on it, and the second shell, which was also the last shell, which will contain 5 electrons because nitrogen is in group 5. As a result, the electron configuration for nitrogen is 2, 5. Now we record the information for the two nitrogen atoms. Note that nitrogen has greater than 3 electrons on the last shell. Therefore, nitrogen is a nonmetal atom. In fact, each nitrogen atom has 5 electrons on the last shell, and the first shell contains a maximum of 2 electrons each. Step 2, draw the nucleus and empty shells of the atoms involved in bonding with their outer shells overlapping. Step 3, fill the inner lying shells with electrons. Note that both nitrogen atoms contain one inner lying shell, which has a maximum of 2 electrons each. Step 4, place bonded or shared electrons in the overlapping region, then put any remaining electrons on the area of the shell outside of that region. Each nitrogen atom has 5 electrons on the last shell. To provide a visual, we have placed the 5 valence electrons, those are the electrons to be placed on the last shell, next to the information for the atoms. Based on the electron configuration rules, the second shell is stable when it holds a maximum of 8 electrons. Therefore, nitrogen needs 3 more to make 8. Remember, an atom will only share the number of electrons it needs to become stable. Consequently, the first nitrogen, that's the one on the left, will share 3 of its 5 electrons with the second nitrogen. The shared electrons are placed in the area where the shells overlap. After sharing 3 of its 5 electrons, the first nitrogen has 2 electrons remaining, which are placed on the shell outside the overlapping region. Since the first nitrogen atom shared 3 electrons with the second nitrogen atom, the second nitrogen atom will share 3 of its 5 electrons with the first nitrogen atom. The shared electrons are always placed in the overlapping region. After sharing 3 of its 5 valence electrons, 2 valence electrons are remaining, which are placed on the portion of the valence shell outside of the overlapping region. At this point, all the valence electrons for both nitrogen atoms have been placed on their last shells. Step 5, count to ensure that the last shell of each atom involved in covalent bonding contains their maximum number of electrons. Remember that the inner lying shells already contain their maximum number of electrons, so our focus is only on the last shells. Recall that the electrons shared are counted for both atoms. Starting with the nitrogen on the left, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the first nitrogen atom now has a maximum of 8 electrons on its shell, resulting in the stable electron configuration of 2, 8. We do the same for the second nitrogen atom, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the second nitrogen now has 8 electrons instead of 5 and has achieved a stable electron configuration of 2, 8. Step 6, represent the covalent bond as a stick diagram. Remember, each pair of shared electrons is a covalent bond, and we use a line to represent a pair of shared electrons. So we will write the symbols of the atoms in the order in which they bonded in the illustration, nitrogen followed by nitrogen. Remember to leave sufficient space in which you will draw the lines representing the covalent bonds. So let us check to see how many pairs of shared electrons occur between the two nitrogen atoms. 1, so we represent 1 line, 2 lines, 3 lines. When there are 3 parallel lines representing 3 pairs of shared electrons between 2 atoms, this is called a triple bond. Also, this is what the dot and cross diagram would look like without the inner lying shells with electrons. We have now completed the third example of covalent bonding, which illustrates the formation of the triple bond. So let's do a quick summary of the lesson which we have just completed. Note that atoms bond to obtain a stable electron configuration. The covalent bonds are formed between nonmetal atoms only. Covalent bonding involves nonmetal atoms sharing valence electrons. The atoms involved in covalent bonds will only share the number of electrons they need to become stable. A pair of shared electrons is called a covalent bond. Covalent bonds are either single, double, or triple bonds. The binding force in the covalent bond between two atoms is the attraction of the nuclei for the shared electrons. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. What type of atoms are involved in covalent bonds? A. Metals only. B. Nonmetals only. C. Metals and nonmetals. D. None of the above. The answer is B. Nonmetals only are involved in covalent bonds. Question 2. What type of covalent bond is formed when two atoms share 3 pairs of electrons? A. Single bond. B. Double bond. C. Triple bond. D. Quadruple bond. The answer is C. Triple bond. Recall that each pair of electrons is a covalent bond. Therefore, 3 pairs of electrons would be 3 covalent bonds, which is a triple bond. Question 3. Atom X shares 1 electron with atom Y to become stable. How many electrons did atom Y share with atom X? A1, B2, C3, D4. The answer is A. 1 electron. Recall that an atom will only share the number of electrons that was shared with it. So if atom X shared only 1 electron with Y, Y would share only 1 electron with X. Question 4. An oxygen atom has 6 electrons on its last shell, which is its second shell. Identify the dot and cross diagram that correctly represents the covalent bond between 2 oxygen atoms. Is it option A, B, C, or D? The answer is D. Since oxygen has 6 electrons on its last shell, which is its second shell, the second shell can hold a maximum of 8 electrons, which means oxygen needs 2 electrons to become stable. As a result, it will share 2 of its electrons from each of the oxygen atoms. So we see we have 2 dots and 2 crosses. And then after sharing 2 of the 6 electrons, the remainder of the shell outside of the overlapping region should have a total of 4 electrons specific to each atom. Question 5. What is the binding force in a covalent bond? A. The attraction between the ions. B. The attraction between the nuclei and shared electrons. C. The attraction of the nuclei for the inner-lying electrons. C. The attraction for the nuclei. C. The attraction of the nuclei for the inner-lying electrons. D. An electrostatic force between the atoms. And the answer is B. The binding force in a covalent bond is the attraction between the nuclei for the shared electrons between them. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.